Now, in reality, the reason I didn't write a colon here is because this is not the way I want to define it. This is just the way I want it to turn out. I want it to end up kind of satisfying this equation. But we could actually define it in a much, much simpler way. Namely, we can define a plus b in the following way. What it assigns to any path is just a of that path plus b of that path, which is still integer valued. And as we talked about, it still has the property that it assigns 0 to all but finitely many paths. So that's really the definition. It's just like adding any functions. This is consistent with the definition of adding any functions. If I have any function from any set into a vector space, and any second function from that set into that vector space, as long as V is a vector space, actually it doesn't even have to be a vector space, actually, a group under addition is good enough. Anything that forms a group under addition. And then S can be any set at all. It doesn't even have to have any structure. It just has to be non-empty. But it doesn't have to carry with it any mathematical structure. So it doesn't have to have like an addition operation on it or anything. It could be like the set of all cows or the set of all erasers or whatever. But yeah, you can define f plus g in general as a new function from S into that group. A group, G is a group under addition. And addition is always assumed to be commutative. Otherwise we wouldn't write it as addition. It doesn't have to have any specific meaning. It doesn't have to mean like adding numbers. It could mean adding vectors or adding matrices or adding anything. But it doesn't have to have anything to do with traditional numerical addition. It could just be any operation that forms a group, as long as it's commutative. We reserve the plus sign to always deal with commutative operations. We'd never write any operation as a plus if it's not commutative. So basically what I'm saying is that it's a commutative group, otherwise known as a abelian group. An abelian group is one in which the operation is commutative. Okay, anyway, so what does a group mean? It just means that it's closed under the operation. The operation is associative, and it happens to be commutative, so simply because I'm assuming it's an abelian group. But every group has an associative operation, and then of course there are inverses. Oh, sorry, there's an identity element, which is typically written as 0 in the additive context. You see, if you're writing the group with a multiplicative notation, where the operation is written as a product, then we would typically call the identity element 1. So these two notations go together. But if we're writing the operation as a plus sign, which we reserve only for commutative operations, then we would write the corresponding identity element as a 0. Okay, and then there are inverses, or negatives, which we would write with a minus sign in front. Okay, so in the multiplicative context, we would write the operation that way, we'd write the identity that way, and we'd write this for the reciprocal. But in the additive context, we write these. Okay, anyway, so what is the general definition of adding functions? Here it is. For any element little s in the domain big S, we define this as just f of s plus g of s, where this addition is being done in G, in the group. Because f of s is going to be some element of G, and then g of s is also some element of capital G. Any two elements of the group can be combined via addition, and it will give you a new element of that same group. So it's a very, very general definition of what's called function addition. And this operation here of addition of chains, addition of formal sums, really. I haven't gotten to chains yet. But addition of formal sums counts as a special case of functional addition. Okay, it's really just a special case of functional addition where the group happens to be the integers, which is certainly a group under addition. In other words, ordinary numerical addition. So I'm basically taking my G here to be the integers under standard addition, standard numerical addition. And that's certainly a group. Right, now you see that the two definitions are equivalent to each other. This definition here, which is ultimately what I'm going to take as my definition, is consistent with this formula that we wanted to come out here. Because, after all, the number displayed in the square brackets next to gamma is the value at gamma. That's the way this notation works. Whatever the value of this function is at gamma, we display that in square brackets right next to gamma. So basically, a plus b evaluated at gamma is by definition a of gamma plus b of gamma. And that's just exactly what this definition says here. So the reason I'm emphasizing this is simply to show you that this is not some exotic new definition of addition that only applies to formal sums. This is it's just a special case of a much more general notion of addition, which is just addition of functions. So by regarding a formal sum as a function, we see that it gives rise to a very natural addition operation. Because functions can always be added as long as they map into a group. And the integers do indeed form a group. Okay, so anyway, that's one thing. And then the scaling operation can be treated very similarly. You see, again, if I have any function at all, let me do this in gold again. If I have any function at all from any set into a group, additive, like commutative or abelian group, then if I take... okay, now here a group is not sufficient. We need a vector space. So let me say it like this. Suppose I have a vector space, which has an addition operation on it, as well as a scaling operation, which I'm just going to write as a dot. So I'm assuming here that V is a vector space. And plus denotes vector addition on that space. And by dot, what I mean is scaling. So don't confuse that for like a product operation. It's not the product of two vectors. It's the product of a scalar times a vector. Okay, well, let's say the scalar I write is alpha. And the vector as v. So it's a scaling operation. So let's say S is, again, a non-empty set. It doesn't have to have any particular mathematical structure on it. But again, V is a vector space. And I have some function from S into V. Well, then it makes sense to define like alpha times F, where alpha is any real number. And the way you do that is you just define it as like the value that it takes at little s, which is an arbitrary element of big S, is by definition alpha times f of s. And that makes sense in the vector space, because this is just some vector in V, and then alpha is some scalar, so you can scale the two. You can multiply them as in scaling, and that's going to give you another element of V. So that defines a map alpha times f, which also goes from S into that same vector space. Now, that's a little bit more specialized than what we have. See, we have a situation where the scalars really should only be integer valued, because, like, let's say I have some formal sum of paths. So these coefficients here are integers. But you see that if I scale that by some real number, let's say alpha is some real number, right? And then when I scale alpha, or a by alpha, what I would like to say is that the alphas are going to move into the coefficients. Right? Just as addition is done at the level of the coefficients. You really add the corresponding coefficients. So you perform the addition at the level of individual coefficients. Well, in the same way, we would like to perform the scaling operation at the level of the coefficients. We should just take all the coefficients and scale them by alpha. But you see, this doesn't make sense, because if alpha is some arbitrary real number, not an integer, then this product here may not be an integer. Possibly, anyway. And that means that this would possibly not be a formal sum. So we really need to limit these. We should limit the alphas to be integers. Now the problem is that the integers are not a field. So with a vector space, it's assumed that the scalars, like the set of scalars that are used with the vector space, V, are assumed to form a field. That's part of the definition of a vector space. That's all built into the definition of a vector space. And what is a field? We call the field big F. Okay, so a field is just a set that is closed under two operations, addition and multiplication, and it has like a 0 element and a 1, which are distinct, and it obeys all the usual rules of algebra. So, for example, addition is commutative and associative, has an identity element 0, and it has inverses, which are negatives. Also, multiplication is commutative and associative. It has an identity element 1, which is distinct from 0, and it has inverses for everything except for 0. 0 is the only thing that doesn't have a multiplicative inverse. And then you have the distributive law, which connects addition to multiplication. Like, these are related to each other by distributivity. All right, that's called a field, that type of mathematical structure. So for example, the real numbers, with its standard addition and multiplication operations, forms a field. Also the complex numbers, with its standard addition and multiplication, form a field. Okay. Also the rational numbers form a field. So the scalars that we use with a vector space are assumed to form a field. Now, if I relax that requirement and allow the scalars to be a ring instead of a field, then we get something that's not called a vector space, but rather called a module. So a module just replaces the scalar field with a scalar ring. And what do I mean by a ring? Okay, a ring is like a field. It's a mathematical structure consisting of a set, which I'll call R, but that's not the reals. I'm just using R as a letter to denote a ring. But it has, again, two operations with identity elements. Okay, actually, some rings don't have a 1. A unital ring is a ring that has a multiplicative identity. So, okay, unital ring will have a 1. And the 0 and the 1 are distinct, by the way. Part of the definition is that the 0 and the 1 are distinct. The only difference with a field is that multiplicative inverses don't necessarily exist. They can exist, but they don't necessarily exist. So in a field, every element of that field, except for 0, has a reciprocal. But in a ring, there may be other things that don't have a reciprocal, other than 0. Okay, so we just loosen up one of the properties of a field, but all the other properties are still there. Like, it still has to have a distributive law to relate addition and multiplication. Right? Addition is still commutative and associative. Multiplication is still commutative and associative. Addition has an identity and inverses. Like, everything has a negative. So addition has all the same properties in a ring as it does in a field. Every element of the ring has a negative, with no exceptions. But multiplicatively, you may have some things having multiplicative inverses and some other things not having multiplicative inverses. So 0 is not the only thing that might fail to have a reciprocal. There may be other non-zero things that also fail to have a reciprocal in a ring. So yeah, if I let the scalars be form a ring instead of a field, then the same concept of vector space is then called a module over that ring. So instead of a vector space over the field, a vector space over the field F, we have a module over this ring, okay? Now, in that case, the scalars are going to come from a ring rather than the reals. Right? Instead of the scalars being real, the scalars are now going to come from this ring. And so the V here is not necessarily a vector space, but a module. Let me call it M for module. So you see, if I have any mapping F from any arbitrary non-empty set into a module, then I can define scaling for that map, as long as alpha is an element of that module. Sorry, an element of the ring of scalars. Whatever the ring of scalars is for that module. Okay. So in our case, what I'm saying is here that the formal sums, like the set of formal sums over U, forms a module over the ring of integers under the standard addition and multiplication with the standard 0 and 1. Right, the integers form a ring. You can always add and multiply, like it's closed under both operations. Both operations are associative and commutative. The identity elements, 0 and 1, are certainly distinct, and they both belong to the integers. The distributive law holds, because this is just ordinary addition of numbers and ordinary multiplication of numbers that we're talking about, so we already know that the distributive law holds. Every integer has a negative, which is an integer also, so no exceptions to that. The only thing that doesn't work is that, like, some integers don't have reciprocals, which are integers. 1 and negative 1 have reciprocals, which are integers. But, for example, 2 doesn't have a reciprocal in the set of integers. It has a reciprocal in the set of reals, 1/2, but it doesn't have any reciprocal in the set of integers. So it's just a ring, it's not a field. But this thing forms a module over that field, and we can define, so our definition is going to go as follows. If I have any integer, let's say alpha, and I have any formal sum, a, I will define alpha times a exactly the way it's done in general. The general definition of scaling in this scenario here is this formula right here. So I'll just use that very same definition of scaling. It's alpha times a of gamma. And that's going to give the coefficient of gamma. So in other words, if I have this expression for a, where all the values are written inside brackets as coefficients, what this is telling me is that alpha times a can be written this way. We just put the alpha inside here. We multiply, in other words, by alpha at the level of the individual coefficients. And that does yield an integer, because alpha is an integer, and then a of gamma is an integer. So the product of two integers is necessarily an integer. And also let's notice that this does indeed belong to the set of formal sums. The answer, the result of doing this does indeed belong to the set of formal sums, because we have to check that the coefficients are almost always 0. Let's check that. It's easy to check. This is 0 whenever a of gamma is 0, which happens whenever gamma is outside of some finite set. So therefore these coefficients are also 0 outside of a finite set. And so yeah, we have a legitimate expression, like all the coefficients except for a finite number of them will be 0, because they're just going to be alpha times a bunch of zeros. The only way you could ever get a non-zero coefficient is if the original a of gamma was also non-zero, and that only happens for finitely many gammas. So this does indeed define a legitimate operation, and you can do that operation either here, outside of the a, or you can do it inside the brackets, term by term. So just a quick example. Let's say I want to, oh, and by the way, notice that now I don't need any brackets around this alpha. Originally, when I introduced this, I said we should put brackets around the alpha. But now that we see the connection to the general concept of scaling, completely general concept of scaling functions, which was this, we don't really need the brackets anymore, because the general notation doesn't involve brackets. Like this general notation for scaling doesn't involve brackets. All right, so let's say I have, do an example. Suppose this is my a, my formal sum a, and I want to multiply that by, let's say, -2, some integer. And the way you do it is just put the -2 factor inside all the brackets. Okay, so it's very, very easy. These are easy operations to perform. But the point of this whole discussion is simply that the set f of u is not just a set, it carries with it an algebraic structure, namely the structure of a module over the ring of integers. So in other words, it has an addition operation on it and a scaling operation on it. Scaling by integers. Great. Okay, good. The only problem, okay, right, so now we have to ask ourselves this question. What is the point of any of this? Why introduce these formal sums? Okay, the answer is that we already have an operation on paths called concatenation. Remember, we have this operation of concatenation on paths, which says that if I have a path, gamma 1, and I have a second path, gamma 2, that are linked, these paths have to be linked in that order. In this order, meaning gamma 1 first and then gamma 2. What that means is simply that gamma 1 at its terminal point, or final point, is the same as the initial point. of gamma 2. Well, then we can define a new path, gamma 1 concatenated with gamma 2. And that's, again, a path also in U, as long as the original two paths were also in... Sorry, that's a path. Right? As long as the original two paths are in U, because if this is my region U, right, and gamma 1 and gamma 2 are both in there, what that tells me is that the trace of gamma 1 is entirely in U. The trace of gamma 2 is also entirely in U. But remember that the trace of the concatenation is nothing but the union of the two traces. So since each of them is in U, their union is also in U. So the concatenation operation exists in the set of paths. But it has certain limitations. Namely, for that to be a path, the two things have to be linked. If I just have any two paths, both in U, let's say I have a region U, and I have just two arbitrary paths that are both in U, then the concatenation just doesn't exist. I mean, you can still define it, like the same formula still applies. You can still define it as some function of t, but the problem is that function of t is not a path, because it's discontinuous. It will jump suddenly in space, right, like instantaneously. So it's not a path, is the point. Even though gamma 1 and gamma 2 do belong to the set of paths in U, their concatenation does not. So it's a flawed operation in that sense, and you can't just take two arbitrary elements of this set and combine them. The two elements have to be very specially placed relative to one another. They have to be linked. So that's one flaw in the... Right? The other flaw is that it's not a commutative operation. The concatenation of these two is not the same as the concatenation of these two. In fact, they're not even both defined, usually. Like, if gamma 1, if this concatenation is defined, it means that you have to have this linking condition. But then this other concatenation here is generally undefined. Because if you go along gamma 2 first, then you would have to jump to get to the initial point of gamma 1, and you're not allowed to do that. It's not a path. Right? So tracing along gamma 2 first, and then tracing along gamma 1 does not yield a path. Now, there are certain cases where both are defined. Right? So, for example, let's say I have just 2 points, P and Q, and I'll have a path gamma 1 from P to Q, and then another path gamma 2 that goes from Q to P, right? So you look at the two concatenations, they're both meaningful, but they're not the same. Because one of them begins at P and ends at P. The other one, where you trace along gamma 2 first, that begins at Q and then ends at Q. They cover the same points in the same direction. So there is a relationship between these two. Namely, they're equivalent. You can reparameterize one of them to get the other, but they're not the same. So anyway, the point is we don't have a commutative operation here. So the operation is only partially defined. The operation of concatenation is only partially defined in the sense that you cannot take two arbitrary elements of this set and perform that operation on them to get another element of that same set. The set is not closed under the operation. Okay, that's one problem. And then the other problem is it's not a commutative operation. Now, why is that even problematic? Okay, it's not really problematic. It's just that, remember, we have this rule. If f is continuous, let's assume here that f is at least continuous on the region U, so that the Riemann integrals will make sense. But there's this rule that says that the integral along the concatenation is the sum of the integrals along the individual pieces. This is also provided that gamma 1 and gamma 2 are linked in this order, so that the concatenation even makes sense. Right? But yeah, there's this rule. But now you see that swapping gamma 1 with gamma 2 does not affect this side of the equation. If I swap gamma 1 with gamma 2, under that swap, the two terms will just swap. But since there's a plus sign between them, it doesn't affect that side. And yet, you can't do that swap here, because the concatenation just may not be defined as a path. So for that reason, it makes sense to try to replace concatenation with some other operation that's very similar to it, but is commutative. And so if I can basically replace concatenation with some other operation, let me call it star temporarily, which is a commutative operation that's always defined. So like, you can swap gamma 1 with gamma 2, and it's always well defined, meaning that gamma 1 and gamma 2 can be completely arbitrary. They don't have to be linked. Yeah, then we're going to get this very nice pattern that, the integral of f on the combined path is going to be the sum of the integrals on the individual pieces, and both sides are invariant under the same swap. Both sides of the equation should be invariant under the same swap. Right? So because it doesn't, aesthetically, it's not very nice that one side of the equation should be invariant under a certain interchange, whereas the other side of the equation doesn't seem to be invariant under that same interchange. So that's hinting that there's something deeper going on here. The asymmetry, in other words, in this equation, the fact that one side of it is perfectly meaningful or sensible under an interchange of the two paths, whereas the other side does not appear to be, is hinting that that's just an appearance, it's not a reality. That the reality underneath, at a deeper level, is that there must be some other operation we can do which is commutative, but that somehow encompasses concatenation. And we're going to build that operation. we're going to build that operation by doing the following thing. We're going to adopt the rule that if I have two paths in U, right, two piecewise smooth paths, which are linked so that their concatenation makes sense in this order, right, meaning that you do gamma 1 and then you do gamma 2 right after that. They're linked together. So if I have that, then notice that gamma 1 concatenate gamma 2 is therefore also a path in U, as we just discussed. So we know that already. But what I'm going to say is that the rule is that if I take that new path, gamma 1 concatenated with gamma 2, and put a coefficient of 1 in front of it, so notice that that's a formal sum. And then there's a totally different formal sum, which has this structure. It assigns a 1 to gamma 1, and then assigns a 1 to gamma 2. So notice that these are two completely different formal sums. At the level of formal sums, these are distinct. These are different as formal sums. Let's take a moment to appreciate why that's true. You see, the first one of the two, let me call it A, let me call this one B. A assigns this concatenation the value 1, and it assigns every other path the value 0, if gamma is not that specific concatenation path. B assigns gamma 1 the value 1, and assigns gamma 2 the value 1, and then assigns zeros to every gamma that's not either gamma 1 or gamma 2. So those are two different mappings, right? Those are two completely different mappings. A is not the same mapping as B. So as formal sums, as elements of f of u, they are different. But the rule we're going to adopt is that they are the same, that A and that B are considered the same as chains. So we're going to now start like a new set called script C of U. These are the chains in U. And what are chains? Well, they're just, technically, a chain is an equivalence class of formal sums, where the equivalence relation consists in the rules that are being given now. Okay, here's what I mean by that. What I'm saying is that that A, which assigned a coefficient of 1 or a value of 1 to this concatenation, and then that B, which assigned a value of 1 to gamma 1 and then a value of 1 to gamma 2, those are different in the set script f of u as formal sums, but we consider them equivalent. And, that's my equivalence relation. Equivalence of formal sums. Okay, and we're just going to define, we're just defining equivalence by stating some rules. And one of the rules is that A and B are equivalent when A and B have those two forms. And more generally, let me call this rule number 1. This is part of the definition of equivalence. Part of the definition of the equivalence relation, tilde. I.e., also known as equivalence of formal sums. So rule number 1, more generally, is that if I have a path that assigns, not a path, sorry, a formal sum, that assigns an integer value n to a certain concatenation, and this can be like a k-fold concatenation, but the linking condition has to hold. For that k-fold concatenation to make sense as a path, the pieces have to be linked in the appropriate way, in that order. So gamma 1, then gamma 2, then gamma 3, then gamma 4, and so on. So assuming that we have that linking condition in that order, the formal sum that assigns the integer n to that, and then zeros to everything else, is going to be equivalent to this B, which assigns the value n to each individual lambda j, where j runs from 1 to k. So same value n, but it gets assigned to each individual piece. So you see that in particular, when you take n equal to 1, what it's basically saying is that if I take the n to be 1, so the formal sum in which this has a 1 attached to it and this also has a 1 attached to it is equivalent to the formal sum in which this whole thing has a 1 attached to it. That's roughly what equivalence is supposed to be doing for us. It's supposed to be bringing geometry into the picture. See, let me just say it this way. In this whole theory of formal sums, the geometry of paths never entered the picture. The whole theory of formal sums, including the fact that it's a module, like it has the algebraic structure of a module over the integers, was all purely algebraic. It was all a bunch of algebraic trickery, algebraic, definitions and gimmicks. It had no geometric content at all. It had nothing to do with paths, specifically as geometric objects. We could have formed formal sums out of anything. They didn't have to be paths. We could basically take any object. You can have formal sums of cows, for instance. can assign, that brown cow the value 3, and that red cow the value -2, and that spotted cow the value 5. Then you could write a formal sum, a formal like linear combination. 3 times this cow plus -2 times that cow plus 5 times that cow. And you would still get a good theory. Like this set of formal sums of cows would still be a module over the integers. So it really had nothing to do with the geometry of paths. What we're trying to do with this equivalence relation is we're trying to bring into the picture of formal sums, which is very generic, just a purely algebraic construction, totally generic and having no content, no geometric content anyway. But we're trying to bring some geometric content into it. And the way we can do that is by making sure that this picture here and this picture here, although they're not the same as formal sums, but at least they should be counted as equivalent formal sums, by definition. So you see that there's a formal sum that assigns a 1 to this path and a 1 to that path and 0s to all others. And then there's a totally different formal sum that assigns a 1 to this entire concatenation and 0 to all other paths. Those are different as formal sums because formal sums don't have any geometry within them. It's just a very generic, abstract construction. It can't tell what things are geometrically similar. But the equivalence relation is supposed to fill that gap. The equivalence relation is being defined in such a way that two things that are geometrically very similar are counted as equivalent, as sort of the same. Okay. Now, there are other rules. This is just rule number 1. We're going to get to some other rules that also define the equivalence relation, different aspects of that same equivalence relation. But this is just one piece of the definition of equivalence. So you see that the theory of concatenations is being brought in, is being combined with the theory of formal sums. And by chains, what I mean are just equivalence classes of these formal sums. An equivalence class just means a particular formal sum together with all equivalent formal sums. Take a particular formal sum, let's say A, and also everything equivalent to A. And that gives the equivalence class of A. So let me call that just temporarily, what should I call it? So let me denote it by angle brackets. I'm going to drop this notation eventually. I'll explain. I don't want to have too much notation, too much fancy notation, because the problem with too much fancy notation is that, first, it's bothersome to write down every time. Secondly, when you have hundreds and hundreds of different notations, it's hard to remember all of them. So, there's a lot to be said for elegant notation. But temporarily, let me just write it this way. And the equivalence class, so if A is a particular formal sum, the equivalence class of A under a particular equivalence relation, which is denoted by tilde, would just be, let me denote it like this again, angle brackets of A. And by definition, what it is just all formal sums B that are equivalent to A. Take every possible formal sum B that is equivalent to A, including A itself. By the way, notice that A is going to be equivalent to itself just by definition. We're going to define equivalence that way. You can call that rule 0 if you like. Rule number 0, let's say, is that always A is equivalent to itself for all formal sums. Okay, so that's like the reflexive property. We just build that in by definition. So anyway, you take A, which is equivalent to itself by definition by rule 0, and you also take every other formal sum B, which is equivalent to A. So for example, these two would be in the same equivalence class. Both of them would be elements of this equivalence class, or both of them would also be elements of this equivalence class. See, when A and B are equivalent, then their equivalence classes are the same. And when A and B are inequivalent, then their equivalence classes are different. So you see that the equivalence classes are these new objects that are equal exactly when the original two things are equivalent. So that equivalence can be replaced with equality. That's what the purpose of equivalence classes in mathematics in general. The whole point of using equivalence classes is that sometimes you want to say that if two things are equivalent to each other, then they should be regarded as equal. They should, for certain purposes. Like even though there's a distinction between them, it's not an important distinction within that context. And so if you can define an equivalence relation between them, then you can look at their equivalence classes. And those equivalence classes will be equal to each other exactly when the original objects are equivalent. So it's a way of replacing equivalence by equality, by true equality. And so that's what I'm going to say are chains. There's equivalence classes of formal sums where the equivalence relation is defined by certain rules. And those rules are designed to connect geometry, the geometry of paths, into the structure of formal sums, which in itself has no geometric content. So we have to give it geometric content by making these rules and defining this equivalence relation. Okay? Now in practice, so this is like the mathematically very clean way of defining things, but in practice, we usually don't distinguish between a formal sum and its equivalence class. We sort of have a vague identification of these two, but we just write the equal sign instead of the equivalent sign. So instead of having a notation, and let me clarify it this way. The very careful thing to do is to distinguish between A and its equivalence class, but to have this symbol. And if you want to write that with an equal sign, you have to include both of these brackets. Okay, the less careful way of doing it is to basically make no distinction between A and its equivalence class, but merely to write equivalence as equality. You just write it as if it is an equality. But you have to understand that what that's doing is it's relativizing the equal sign. The equal sign is relative to this set. As chains, they're equal. whereas as formal sums, they're not. Okay, so that's another notation, another like way to go notationally would be to say, let me write this over here. Okay, with rule number 1 here, what I'm really saying, you can think of it this way, is that although A and B are different in the set f of u, they're different as formal sums, but by definition of equivalence, by definition of like this equivalence relation, A equals B in the set C of u, because the set C of u really consists of just the equivalence classes. And since A and B have the same equivalence class, right, being equivalent to each other, they have the same equivalence class. But we just don't bother writing the brackets. If we were being very careful, we would write the equation this way, and then C of u would consist of those equivalence classes. But the careless way, or let me not call it careless, just the less careful way to write it, which is a little more elegant, a little more kind of free-flowing, is to say that, okay, C of u also consists of those same objects, except that the equality relation is different. We redefine equality, so that in C of u, you have the same exact objects, which are just the formal sums, but you're equating some of them. You're considering them equal, even though they're, as formal sums, they're different. Okay, so either way, it doesn't matter. I'm going to say this. I'm going to just say that those formal sums are equal as chains. And a good way to do that is to put the C as a subscript on the equal sign. So instead of writing equivalent, I'm just going to write them as equal, but with the C under the equal sign. And maybe I'll just make it an ordinary C, just because it's easier to write. So that's called chain equality. And it just means the same thing as equivalence. Okay, so as chains, they're considered equal. And it really just means equivalence. But we just write it as an equal sign. And this helps us to avoid the need for, the angle brackets, the equivalence class notation. But that's really there, kind of in the background. We're just not writing it. Right, now in practice, I just write an equal sign. I don't usually write the C underneath it. But once you get used to this idea, like no confusion can arise. Okay, let me show you a little example. Let's say I have this picture where I have 3 paths that are linked appropriately in this order. Right? Gamma 1, then gamma 2, then gamma 3. And I look at this concatenation. Or maybe I'll actually do something else. Like I'll do this. Yeah, so let's look at this. So this is a particular formal sum where the value 2 is assigned both to this path and to this path. Now what I'm saying is that this is chain equivalent, chain equal to, also called equivalent to, the formal sum that just assigns a 2 to each piece individually, and also chain equal to the formal sum that assigns the threefold concatenation, the value 2. That is, this whole thing gets assigned a value 2, and then everything else gets a value of 0. So here I have like 3 different formal sums. They're all different as formal sums, but they're all the same as chains. And then the only leap you have to make is that instead of writing this relation as an equal sign with a C under it, or as an equivalent sign, we just write them as ordinary equal signs, just for brevity. Just for brevity, we write equals with nothing under it. But you have to interpret it correctly from the context. See, if I write an equal sign between those two, let's say between these 3, I just write a plain equal sign, you can see by the context that I can't mean that they're literally equal, because they are different as formal sums. So what I must mean is that they're equivalent. The context sort of tips you off to that. Now, of course, there is another explanation, which is that I just made a mistake. Right? It's certainly possible that a person writes down an equation that's just mistaken, it's just false by accident. But if we just are charitable and we assume that everyone's correct in everything they write down, you can interpret that as meaning that, okay, I can't mean literal equality since they're obviously not equal as formal sums. So the equal sign must have a different meaning, and that meaning is equivalence. And so the context kind of tips you off to that. It's better to do this, even though it might be a little bit, let's say, disappointing that you would take 2 things that are mathematically distinct and pretend that they're equal. But we're not really pretending they're equal. We're just using a convenient symbol. We're just using the equal sign. But it is very convenient. It's very convenient to do this, because having to remember to write the equivalent sign every time is a bit of a pain. So, okay, as chains, these 3 are all equal. But as formal sums, they're not. Okay, and technically, what it really means is that the equivalence class of this is exactly equal to the equivalence class of this is exactly equal to the equivalence class of that. But I just don't want to have to write the brackets every time. So we just kind of omit them. But it has to be understood from the context that that's what we're doing. Okay, great. So anyway, that's a set of chains. But there's other rules. So I've only partly defined the equivalence relation. I'm going to talk about the other rules now. Okay, so we have rule 0, and we have rule 1. Whoops, I did it. I wrote equals here, and that's good. Like we want to write that, but for now, just to be very careful, because the rules are supposed to be defining this symbol. So when I actually state the rules, I'll just use that symbol. Again, the rules are just a way of defining the equivalence relation. So in those definitions, I really should just use the appropriate symbol that is actually being defined at this moment. But then later, once it is fully defined, we can then just write it as if it's an equal sign, and the context will tip us off. Okay, well, what about rule 2? So that is going to relate to the concept of reversal, because that's another geometrically important idea. Not only concatenation, where you link two paths that happen to be linked, right, into one bigger path, but also the idea of reversal. If I have a path, gamma, it has a reversal which covers the same points in the opposite direction. We wrote that as gamma upper minus. Just to remind you how it's defined, we defined it as the original gamma with negative t plugged in. And the domain, if the original gamma had this domain, a to b, then gamma upper minus has this domain, minus b to minus a. Okay. So basically we're running time backwards, so that the parameterization begins at the terminal point of the original gamma and ends at the initial point of the original gamma, traversing it in the reverse direction. So that's called reversal. That's a geometrically important notion, and notice that it's reflected in terms of integration. So remember that concatenation had this property where it's reflected in the world of integrals. Basically, concatenation gets represented in the world of integrals by a plus sign. And because plus is supposed to be commutative, that led us to ask, why isn't concatenation commutative? Now you see, I want to use that opportunity to point out that rule number 1 solves that problem. Because once we consider equivalent things to be equal, then you see that the ordering of this concatenation becomes unimportant, because this formal sum, the ordering is unimportant. Now I probably didn't say that earlier, but with formal sums, you can reorder the terms however you like. I can also write any of these by rearranging their terms. So for example, I could write this as 2 gamma 2 plus 2 gamma 1 plus 2 times gamma 3. Also, it gives the same value, because it's still the same mappings, still the same collection of mappings. Gamma 2 still maps to 2, gamma 1 still maps to 2, gamma 3 still maps to 2, and then everything else still maps to 0. So the order in which you write the terms is unimportant. And so yeah, once we write it as a formal sum, then it's clear that the order in which we write the terms is unimportant. So we take something that is not commutative and sort of regards it as something that is commutative through this equivalence relation. So that's part of what the equivalence relation is doing for us, is it's solving the commutativity problem. But the reason there is a commutativity problem at all, the reason there's a commutativity problem in the first place, is because of this relationship, which tells us that there's a connection between concatenation at the level of paths and addition at the level of integrals. Okay. Well, there's a similar relation with reversal. You'll remember from earlier in the course, we had this general identity. Again, provided f is continuous on the region. And the path is a path in that region. Right, so you see that there's a certain operation at the level of paths, which is the reversal operation, that gets reflected at the level of integrals as a factor of -1. So we would like to embed that fact into our theory as well. So just as we needed a special rule to relate concatenations to formal sums, we're also going to need a special rule to relate reversals to formal sums. And the rule is very clear. It goes like this. If I take the reversal, gamma upper minus, and I attach a coefficient of n to it, we're going to consider that to be equivalent to taking the original gamma and attaching a coefficient of -n to it, which is still acceptable because it's still an integer. If n is an integer, then -n is also an integer. And so we're going to consider those two to be equivalent. This way, reversing the sign of the coefficient is equivalent to reversing the path itself. Notice I said equivalent to, not exactly the same, because these two are definitely not the same. These are not the same as formal sums.